proceed with the concept of dynamic hashing now. Stated, the database may grow or shrink with respect to the time. So database may grow in size, or sometimes database may shrink with respect to size as time passes. So dynamic hashing is the good technique for such kinds of databases. Those grow or shrink in size, right? So this concept of dynamic hashing allows the hash function to be modified dynamically, right? So one of the techniques under dynamic hashing is known as extendable hashing, and this technique we are going to discuss next. Extendable hashing. So this is one kind of dynamic hashing techniques, right? It is one form of dynamic hashing. So let us see few important details about this technique, extendable hashing, right? Let us see the process first, and then I'll go for illustration of this dynamic hashing with one example, right? So if you feel any difficulty in understanding the concepts, please raise the questions. So in extendable hashing, we select a hash function such that it generates a value over a large range. So typically, we select a hash function which is b-bit integers. So hash function actually produces the integers, and those integers can be represented typically in b bits, and the value of this b is typically 32. What does this mean? This means that I am using a hash function h that produces a number which is 32-bit long. Right? Now, what next? At any time, we are making use of only a prefix of the hash function to index into a table of bucket addresses. So what does this mean? See, as I stated, my hash function is creating a number which is 32 bits long. Let us assume that first few bits of this 32-bit long number are say 1010, 1100 and so on, right? So these are the first few bits, first 8 bits of a 32-bit number. Okay, so at any time we are using a prefix of the hash function. What does this mean? This means that we are not making use of all those 32 bits at a time, but we are making some small number of bits, the prefix. So prefix means some initial bits we are making use of to create the index or to store my file using hash file organization technique, right? So instead of making use of all 32 bits, at any time we are making use of only a prefix. Means initially I may use only 1 bit, then I may use 2 bits, then I may use 3 bits and so on, depending on the requirement, right? Here we are introducing data structure, and that is known as bucket address table. Bucket address table. Now, the length of the prefix, let us assume that the length of the prefix is I bits, and I is between 0 to 32. What it means? It means that I'll be using 0 bits, I'll be using 1 prefix bit, I'll be using 2 prefix bits and so on. So I'm saying that this is my I. So how many bits I'm using? That is the length of the prefix. Length of the prefix. So I'll be using 1 bit, then length of my prefix is 1. If I am using 2 bits, then length of my prefix is 2. So I denotes the length of the prefix. So one more data structure that we are making use of is bucket address table. So if the length of my prefix is I, then the bucket address table size is always 2 to the power I. So initially my I is 0. Initially I is 0. So bucket address table size is 2 to the power 0, that means 1 initially. Okay, now if I becomes 1, then bucket address table size would be 2 to the power 1, so 2 and so on. So this is how there is a relation between length of prefix bits, those we are using, and the size of bucket address table. We are going to see what it is actually with example and how this structure looks like. But initially, we should understand few terms, and that is why we are discussing this. Now, the value of I, that means the length of prefix, grows and shrinks as the size of the database grows and shrinks. Right? So, if the size of the database grows, then I need to increase the length of prefix I. If the size of database shrinks, then I need to decrement this length of prefix I. Right? So, value of I grows and shrinks as the size of database grows and shrinks. Next, multiple entries in the bucket address table may point to the same bucket. We will see what does this mean with example. Right? Thus, the actual number of buckets is typically less than 2 to the power I. So let us see now how my extendable hash structure looks like. So see here in this slide, we are having this as my bucket address table. This is my bucket address table. Associated with this bucket address table, I am having this hash prefix denoted as I. Right? Now, what we stated, I is actually the number of bits, those we are using. So for this particular example, our I value is 2 bits. So if I am making use of first 2 bits of my hash function, then in my bucket address table, I'll be having 2 to the power I entries. So size of my table, this is my bucket address table. So size of my bucket address table is always 2 to the power I. Here we are using 2 bits, I equal to 2. And that is why the size of table is 2 to the power 2, that means 4. Meaning we are having here 4 entries in our bucket address table. Right? So this first entry is meant for 00, second entry is meant for 01 because we are using only 2 bits. Third entry is meant for 10 and the fourth entry is meant for 11. Right? Now, see here, we are having several buckets. Every bucket is also associated with an integer. So this bucket 1 is associated with some integer I1. See here, this bucket number 2 is associated with some integer, say I2 and so on. So this number that is associated with the bucket gives us the length of the common hash prefix. Length of the common hash prefix. What does this mean? In this particular structure, see here, the value of I is 2. The value of I is 2. And these first two entries are meant for the prefix 00 and 01. Both these entries are pointing to the same bucket. What it indicates? It indicates that this bucket is having associated this value I1, which is equal to 1. What does this mean? This means that only out of those 2 bits, only 1 bit which is common, that is 0. No? So only this bit is being used for this bucket. Right? Here, see here, this entry for 10 is pointing to 1 bucket. What does this mean? This means that this prefix length is 2, I is 2, and this I2 is also 2. This entry 11 is also pointing to a separate bucket. This means that here my I is 2 and I3 is also 2. So whenever it happens that this integer that is associated with a bucket is less than I, then it happens that more than 1 entries from my bucket address table are pointing to the same bucket. Are you getting me? Whenever this integer associated with a bucket is less than this length of prefix I, this indicates that more than 1 entries from my bucket address table are pointing to the same bucket. If my I and this ij, let us assume that this bucket is ij. So if I is equal to ij, what it indicates? It indicates that every pointer, every entry in bucket address table or this particular entry in bucket address table is pointing to a single bucket. So the number of bucket address table entries that point to the bucket j is 2 to the power I minus ij. I'll repeat, the number of bucket address table entries that point to the bucket j is 2 to the power I minus ij. What does this mean? See here, this is my bucket. So let us assume that this is jth bucket. Right? Now, for this jth bucket, I am having ij value that is 1. My I value is 2. So 2 to the power 2 minus 1. So this comes out to be 2 to the power 1, meaning 2. What it indicates? The number of bucket address table entries that point to this bucket are 2. So 2 entries are pointing to this bucket. If I consider that this is my bucket ij, then my ij value for this bucket number 2 is 2. Right? Now, if I compute 2 to the power I minus ij, that means 2 minus 2. This comes out to be 2 raised to 0, which is 1. This means that the number of bucket address table entries that point to this particular bucket is 1. So only one entry is pointing to this bucket. Here also only one bucket address table entry is pointing to this bucket. Whereas here 2 bucket address table entries are pointing to this bucket. Right? Now, this is the basic related to the extendable hash structure. So how actually the entries are stored into the bucket and how this hash prefix is being used to dynamically add the buckets into the system or to remove the buckets into the system, it requires now some discussion. So with this basic understanding of extendable hash structure, we are going to proceed now with the steps those we need to make use of for dealing with this kind of dynamic hashing. Right now, as we know, each bucket J stores some value, integer value, and that is denoted as ij. So all the entries that point to the same bucket have the same values on the first ij bits. I'll repeat. Each bucket J stores some value ij. Okay, and all the entries that point to the same bucket have the same values on the first ij bits. What does this mean? Let us go back. See here, associated with this bucket 1, I am having this value I1, that is 1. Right? So what we mean by this 1? My I is 2, so my prefix is 0, 0 and 0, 1 for these two entries, and only first bit I1 is 1, meaning only first bit is being used to store the records into this bucket. So if the hash function is having the first bit as 0, right? It happens for both of these entries, then all such records will go into bucket number 1. I hope you must have understood. So prefix length is 2, and out of these 2 bits, only 1 bit is being used for this bucket. And that is why these 2 entries for which the first digit or first bit is common, that is 0, are pointing to this bucket, where this bucket is considering only 1 bit, the first bit, which is same for these 2 entries. Right? So this is what we mean by this first thing. Now, to locate the bucket containing the search key kj, to locate the bucket containing the search key kj, what we are going to do is we are going to compute the hash function for this search key kj, which will produce the result x. And what this result x is? It is a 32-bit long number. Right? Now, what we are going to do next is we are going to use the first I high order bits of x as a displacement into the bucket address table, and we are going to follow that pointer to the appropriate bucket. What it means? Suppose I want to search some key kj, and whenever I'm computing the hash function for this search key value, let us assume that I have generated a 32-bit long number, say 00101111, something like that. Right? Now, I am having the extendable hash structure with me. For that structure, I am having the bucket address table. Right? I am having some value I associated with this table. Let us assume that this I is 2. So what we are going to, if we want to search for a particular bucket where we can find the given search key value, first of all, we are generating the hash function, or we are computing the hash for that key value, which will produce a 32-bit number. And then if I is 2, I'll be using first 2 high order bits. If I is 2, I'll be using first 2 high order bits of this generated value x as a displacement into the bucket address table. So if I'm having 0, 0, 0, 1, 1, 0 and 1, 1, 4 entries, right? Then if the first 2 bits are 0, 0, then I'll be referring to this entry in my bucket address table. And whatever is the pointer associated with this entry, I'll be following that pointer. And that pointer will take me to a bucket. Right? So this search key value that I was looking for, I may find that search key value in this bucket. So this is how it is possible for us to locate the bucket which contains a particular search key value. I hope you must have understood. If you are not able to understand, please let me know. So this was related to locating a bucket that contains a particular search key. Now, if we want to insert a record with some search key value kj into the bucket, right? What we want? We want to insert a record now with search key value, say kj. Then what we need to do? So, obviously, the first step is to locate the bucket where we can place that record having the search key value kj. So we are following this same procedure as lookup, and we are locating the bucket where we can put that record having the search key value kj. Let us assume that we have identified that bucket as jth bucket. Right? Now, what next? Now there are two possibilities. First possibility, we are having ample space in that bucket so that we can insert the record directly into that bucket. The other possibility is the bucket is full and it is not possible to insert a new record into that bucket. Right? Now, if there is a room in the bucket J, then directly we can insert the record in that bucket. No issues. Very simple. Right? So we have identified the proper bucket to insert the record with search key value kj. That bucket is having the space. So I am directly inserting the record into that bucket. But if the bucket is full, there is no space in the bucket to insert the new record, then what to do? So if there is no space available in that bucket, then we need to split the bucket. We need to split the bucket, and once again we need to attempt the insertion of the record. Right? Now, how to split the bucket? It is really very important. So now we are going to discuss this procedure of splitting of the buckets. Right? Now, let us see the procedure how to split a bucket J when we are inserting a record with search key value kj. Now, we know two integers, I and ij. What is ij? Ij is the integer associated with a bucket. And what is I? I is the length of prefix, which is used to create my bucket address table. Right? Now, whenever we want to split the bucket, then we need to consider two conditions with respect to these two values. The first condition is if I is greater than ij, and second condition is I is equal to ij. So let us talk about now these two different cases for splitting the bucket. So if I is greater than ij, what does this mean? If I is greater than ij, this means that more than one pointers are pointing to the same bucket j. Right? So once again, I'll be giving you here the example. Suppose we are having four entries here in our bucket address table. And here is my bucket, and these first two entries are pointing to the same bucket. So here my I is 2, and associated with this bucket my value is 1. So ij is 1 and I is 2. So in this situation my I is greater than ij. It indicates that more than one entries, more than one pointers are pointing to the same bucket j. So if this is the case, then what we are going to do? We are going to allocate a new bucket, say z. So we are going to allocate a new bucket. And what we are going to do? And set ij and iz to old ij plus 1. What does this mean? See here, this is my jet bucket and the old value ij for this jet bucket is 1. So I am adding one more z bucket, right? And what I will do simply, I will increment this value of ij by 1. So this will be now 2, and for this also it will be 2. Meaning now this pointer will point to this bucket and this pointer will point to this bucket. So earlier both pointers were pointing to the same bucket. So now what I have done, as I was greater than ij, I have incremented this value of ij by 1, right? And I have added one more bucket. Right? So what will happen? The entries, those begin with 0, 0 will go in jet bucket, and the entries having first two bits as 0, 1 will go into the second bucket. Got it? So once again we need to redistribute the records into these two buckets now. Have you understood the concept? What if I is greater than ij?
Yes, ma'am.
So if I is greater than ij, then what we are going to do is we are going to split the bucket such that we are adding a new bucket z we are incrementing ij by 1 and that number is assigned to both the buckets. And now these two pointers will point to individual buckets. Correct? So this is how we are going to work if I is greater than ij. But please remember, after splitting these buckets, whatever are the records, those were present in my old bucket and the new record that I am trying to insert, all these records will be redistributed again into these two buckets. The old bucket and the newly added bucket. Right? So this is the procedure that we need to follow for I is greater than ij. Now, the second case is, what if I is equal to ij? What does this mean? See here in this example, my I value is 2, right? I want to insert a new record. Okay, and the bucket that is identified to insert the new record, let us assume the bucket that is identified to insert new record is this ij. This is ij. So this is my jth bucket. This is my jth bucket. So I have found out that the new record needs to be added into this jth bucket. Right? Now, the number associated with jth bucket is 2 and my prefix length is also 2. So in this scenario, my I is equal to ij. And even though this jth bucket is identified to insert the new record, this bucket is full. So there is no space to add the record in this bucket. So what will happen? So here my I value is same as my ij value and this bucket j is full. So I need to split the bucket, but the procedure for splitting if I is equal to ij is different. So what I need to do in this situation, what I need to do is I need to increment this value of I. So earlier I had I equal to 2. So I was using only first 2 bits. Right? But now what I will do is I will increment this I value by 1. So now my I value will be 3. So obviously what I am going to do is I am going to double the size of my bucket address table. So if I becomes 3, then my bucket address table size would be 2 to the power 3. So it is 8. So what will happen now? My bucket address table will have 8 entries. So first 3 bits are now used. 000, 001, 010, 011, 100, 101, 110 and 111. So my bucket address table gets doubled, right? And earlier it had 4 entries, now it is having 8 entries. Now what next we are going to do? We are going to replace each entry in the table by 2 entries that point to the same bucket. Next, we are going to recompute new bucket address table entry for the search key kj, and now it happens that I is greater than ij. And once again, we are going to make use of this process if I is greater than ij. So, I will demonstrate this with one example. So, Please concentrate, have a pen and paper with you so that you can also solve the problem with me. Right? So, let's proceed now with a problem. So, let us assume that we are having this instructor table. Or rather, we are having those instructor entries. And what we want is, we want to insert these instructor records into the hash file organization. Okay. Now, here we are making use of this department table as the search key. Department name as the search key. Right? So, we want to organize our data according to department name. Right? And we want to make use of hash structure to store this data. So, what is the search key now? Department name is my search key. So, whatever are the different department names that we are having, these are my search key values. I am using some hash function on department name. So, if I provide this search key value biology to my hash function h, then my hash function is producing 132-bit long number. See here. So for every search key value, we are having a 32-bit long number associated. So this is how we have computed the hash function for the search key department name. Have you understood till this point? What we have some data. We want to organize this data using hash file organization, and the search key that we would like to use is department name. Right? So we have computed our hash function based on these different search key values. Right? And we have got these 32-bit long numbers. Now, what next we are going to do? We are making use of this hash function that we have computed, and we are going to create extendable hash structure to store this data. Right? Let's proceed now. So initially, our hash prefix length is 0 initially. So initially, I is 0. Right? So if I is 0, then my bucket address table will have only one entry, 2 to the power 0. So only one entry. Right? And let us assume that we are having only one bucket allocated. So this pointer is pointing to this bucket, and this bucket is also having associated the integer that is 0. So if this is bucket 1, then this I1 value is also 0. So this is my initial structure. Right? I is 0. So the bucket address table size is 2 to the power 0, that is equal to 1. Right? And this one entry is pointing to one bucket that is initially allocated, and the value I1 assigned to this bucket is also 0, because we are not having any data inserted right now. Okay, now what we want to insert this first record. Correct? Our search key is department name. Our search key is department name, and we want to insert this very first record now in our hash file organization structure. So what we are going to do is we are going to look for the hash function for this department name computer science, because this first record that we would like to insert is having the search key value, that is computer science. So we want to compute now this hash function for department name computer science. Right now, here we are having those values available with us. So we are using now this 32-bit number for computer science. Correct? What we want? We want to insert this first record. The search key for this first record is computer science. Initially, my structure is like this. Right? So I'm having one entry in my bucket address table, and initially my one bucket that is allocated is empty. So what I will do, I will directly follow this pointer and I'll store this first record in this particular bucket. Right? So I'll be storing say 10101 name, department name, and the salary. So I have stored this record in this bucket. Now, the second record comes in. I want to store this record. So right now I am having in bucket address table, I am having a single entry and that is pointing to the bucket. So till this bucket gets full, I'll be inserting all the records in the same bucket. Right? So this record also will go into this same bucket. Okay, for simplicity, for demonstration purpose, once again we are assuming that the number of entries those can be stored in a single bucket are 2. In reality, lots of records we may add into bucket 1. But for demonstration purpose, this is our assumption. The records per bucket are 2. So, till this first bucket gets full, we are going to insert the records into this particular bucket. Now, whenever the third record comes in, this pointer is pointing to the same bucket. So this bucket is full now. Right? This bucket is full, meaning I need to split this bucket. Okay, now this is my value of I and this is my value I1 associated with this bucket 1. Now, in this case, what happens is I is equal to I1. Both are zeros. I is equal to I1. So, what our rule says, if I is equal to Ij, that means only one pointer to the bucket, then what we are going to do is we are going to increment I and we are going to double the size of the bucket address table. So what we are going to do is as I equal to I1, this I gets incremented by 1. So now my I will become 1. So if my I is 1, then what will happen? My bucket address table gets doubled. So now I am having 2 entries here. So the first entry is meant for 1 bit 0 and the second entry is meant for 1 bit, that is 1. Right? Now, what next? I have split this bucket. So now I'll be having 2 buckets. So this is one bucket and this is another bucket that I am having. So this is the old bucket. And this is the new bucket that I have added. Right? Now, what we are going to do? In this bucket, we have these two entries. In this bucket, bucket number 1, we are having these two entries right now, 10101, 12121, comp science and finance, right? And the I1 associated with this till this point is 0. We have incremented now this I, so I becomes 1. This I1 is 0. This bucket is full. We have split this bucket. So what next we need to do is, as now my I is greater than this I0, I need to work according to this process. So I have allocated new bucket, right? Now, simply what we are going to do is, this I1 gets incremented by 1. So I1 equal to 1 now, and for this bucket I2 equal to also 1. First two records are as it is in this bucket. I wanted to add this third record, which is having music as the department. Right? Now, see here, for this music, I am having first bit as 0. For rest of the two records that we already have in this bucket, for computer science, I am having first bit as 1. For finance, we are having first bit as 1. So, we want to redistribute now these records, including the new one. So, this computer science record with the prefix bit as 1 will go into this bucket. So, see here how we are redistributing the records. See what I am doing. So now my bucket address table is having two entries. So separately now this 0th entry will point to this first bucket and this first entry is pointing to the second bucket. Right? Now I want to redistribute these records along with the new one. Computer science is the first record having the ID 10101. For computer science, the first bit is 1. So, in my bucket address table, I'll search for this prefix 1. So, this entry will take me to this bucket and I'll be inserting that record 10101 with comp science in this bucket, bucket number 2. The second record, finance department. So, for finance, the first bit that we are using is 1 because prefix length is 1. So once again in my bucket address table I'll be using this entry associated with this prefix bit 1. So this pointer will take me to this bucket number 2. Right? So this finance record will also get inserted in bucket number 2. The third record, which is music. So the first bit prefix is 0. So in bucket address table, I'll look for this entry 0. And this pointer is pointing to this bucket number 1. So this record, music, will get inserted 15151 and the department music will be inserted into this bucket number 1. So this is how is the structure after inserting this third record. now we have inserted 3 records in our hash file organization scheme. Now, let us proceed. We have inserted this, this and this. So the next record that we would like to insert is from physics department. So this is the present structure that we are having. So whenever I want to insert this particular record, then what I'll do, first of all, I'll see what is the hash code associated with this physics. So right now, instead of showing all 32 bits, here we have shown only first 8 bits. For physics department, the first bit is 1. So what I will do, I will look for the bucket address table entry corresponding to this bit 1. So this entry will point to this particular bucket. Right? Now, what is happening over here? Once again, this bucket is full. Are you getting me? This bucket is full. Where I have redirected. I want to insert the record from department name physics. The hash function for physics is having the bits like 1001 and so on. So the first bit that right now we are referring to is 1. So the first bit is 1. So I'll be moving into the bucket address table and I'll be locating the respective entry for bit 1. So this is taking me to this bucket. This is my bucket number 1 and this is my bucket number 2. So I'm redirected to this bucket 2. But what has happened is this bucket is full. So once again, if the bucket is full, I need to split the bucket. So if I want to split this bucket, then I need to check what is the value of I and what is the value of ij. So this is the value of I, which is 1, and what is the value of ij? I'm right now considering this bucket 2, so this I2 is equal to 1. So my I2 is also 1. So I is equal to I2. I is equal to ij. So once again, I need to follow these steps. So what I need to do is, if I is equal to ij, I need to increment this I by 1 so that I can increment the size of my bucket address table. Then I'll be replacing each entry in the table by 2 entries that point to the same bucket. And in that situation, what will happen? It becomes that now I is greater than ij, and then I'll follow this process of splitting, similar to that we have followed earlier. Now, see here. Have incremented I by 1. So now my bucket address table will have 4 entries because I is equal to 2. So 2 to the power 2, that means 4 entries. So I'll be referring to now first 2 prefix bits. First 2 bits 00, 01, 10, 11. So in the initial stage, what will happen? Only this gets doubled, so 0, 0, 0, 1, 1, 0, 1, 1, and first 2 entries will point to the first bucket and next 2 entries will point to the next bucket. Right? Now, here my I value and my ij value I am looking at. So I value has become 2, but ij values are still the same. Right? Now, what will happen? Physics Now I'll look for first two bits. So now first two bits are 1, 0. So I will look for this entry 1, 0 in this table. So this 1, 0 is pointing to this. This is full. So I is 2, which is greater than I2, that is 1. So I need to split this bucket. So I'll be inserting one more bucket now. Okay, so no issues with first two entries of bucket address table. So first two entries of the bucket address table will point to the old bucket number 1. But now this bucket 2 is split into two buckets. So now I am having this bucket 2 and I am having this bucket 3. So I need to redistribute now these records. Which records? This computer science record, finance record, and the new record that I want to add, that is physics. Okay, so what I'll do, see here, this comp science record. So comp science, first two bits are 1, 1. So see here now, this 1, 0 entry is pointing to bucket number 2 and 1, 1 entry is pointing to bucket number 3. To insert now comp science record in a particular bucket, I'll be referring to, instead of one bit, now my hash prefix is of length 2. So I'll be referring to first two bits. So comp science first two bits are 1, 1. So I'll be referring to this pointer. This pointer takes me to this bucket number 3. So comp science record is placed in bucket number 3. What about this finance? Finance, first two bits are 1, 0. So I'll search for this 1, 0 entry in my bucket address table. This associated pointer will take me to bucket 2, where I'll be inserting this finance record. The new record that I wanted to insert belonged to physics department. So physics department, first two bits are 1, 0. So once again, I'll be referring to bucket address table entry 1, 0. This pointer will take me to bucket 2 and I'll be inserting the new record from physics department into this bucket number 2. So this is how we need to proceed. So we are done with this fourth record. Right? Now, what next? I want to insert this history record. So this is now our structure and we have inserted 1, 2, 3, 4 records. The next record is history. So refer to our hash function numbers. So history, first two bits 1, 1. So I'll refer to my bucket address table. I'll go to this 1, 1 entry. This pointer takes me to this bucket number 3. Here I can find the space. So as the space is available, this next entry for history gets inserted in this bucket number 3. So 3, 2, 3, 4, 3 and the department is history. So directly we are inserting this history record into this bucket. Right? Now, the next is once again physics. So I'll refer to this physics code. So first two bits are 1, 0, 1, 0. It will take me to this bucket number 2. This bucket number 2 is full. So what I need to split this. So while splitting this, what I will do, I will check whether my I and I2 are same. I and I2 are same. So what I need to do, if both are same, I'll increment I by 1. So I gets incremented to 3. So my bucket address table gets increased, gets doubled. So now I'll be having hash prefix length as 3 and I'll be having 8 different entries in my bucket address table. Right? So first 4 entries will point to this bucket. Okay, and next 4 entries depending upon the first 2 bits will point to the respective buckets. Now, as this bucket is full and now my I has become 3 and I2 was earlier 2. So I is greater than I2. So I need to split this bucket such that now my I2 becomes 3. Right? So I'll be utilizing first 3 bits to locate the records and to place the records at appropriate places. So once again, the same procedure gets followed. See here, this bucket and this bucket are as it is. This bucket is as it is and this bucket is also as it is. We wanted to insert the new physics record into this bucket number 2. So this bucket 2 gets split into 2 buckets. So we have added now this new bucket. This I value gets incremented to 3 and 3. So now first 3 bits are being utilized to locate the records. Right? So now these 2 records, finance, physics and new physics. So these 3 records are being redistributed in these 2 buckets now. So let us see this finance. So finance first 3 bits are 101. So we'll be moving in bucket address table to this entry 101. Right? And this 101 will point to this bucket and the finance record will go here. And this 100 entry I am having. So physics first 3 bits are 100. So this 100 will point me to this old bucket wherein I'll be placing 2 physics entries. Right? So this is how we go on inserting the records. So the same procedure gets repeated again and again, and we are having this respective hash structures after inserting the records. So we had 11 records in our table. So all those 11 records are now being inserted like this. So I hope you must have understood the process. I would appeal you to once again go through the discussion and try to implement it on your own. Try to work with it. Try to play with it. So for that, I'll be giving you one exercise that you are supposed to work with. Please take down this exercise and you are supposed to create extended hash table on a file that is containing these search key values. So check the search key values 2, 3, 5, 7, 11, 17, 19, 23, 29 and 31 and come up with the extended hash structure for this particular file with the hash function h of x given as x mod 8 and assume that one bucket can hold 3 records. Use this hash function, generate the bit maps for all those search key values and assume that one bucket can hold 3 records. So accordingly prepare the extendable hash structure with given search key values. Right? So this is the exercise for you. So I hope you must have understood how actually the extendable hashing works and what is the process that we need to follow to place the appropriate record in appropriate bucket. Once again, go through all this discussion and solve the problem that is being given to you. So let's stop today. In the next session, we'll see how to delete the records from this extendable hashing, and we'll compare between the ordered indexing and hashing. And then we'll go for the last concept from this unit, and that is the bitmap index. So we are going to cover all those details in the next session. So let's conclude today. Thank you.